Hello everyone. Welcome to our next session titled Rio Tinto uses hybrid RAG to unlock potential of generative AI with Bedrock. This session is a level 400 session and today you learn more about hybrid RAG on Amazon Bedrock. It's my pleasure to welcome to the stage Benn, Cizauskas and Kisi. Please give them a big round of applause.
Hello, my name is Benn Cizauskas and I'm a Senior Technical Account Manager at AWS. So this is a level 400 session and the agenda is simple. I'm going to talk about hybrid RAG and share some of the learnings from other customers who have implemented hybrid RAG themselves. Key, we'll talk about Rio Tinto's journey and how they approached hybrid RAG with Amazon Bedrock. We hope you walk away after this session with a clear understanding of how hybrid retrieval augmented generation and Amazon Bedrock enables enterprise domain knowledge to your business. Key, over to you.
Thanks, Ben. Hello, everyone. Welcome to attend this session. So my name is Key. I'm the senior machine engineer, works at Rio Tinto. So to kick off this presentation, let me start with the introduction to Rio Tinto and its aluminum business. The story of Rio Tinto, in fact, the story behind the innovation we're here to explore today. Rio Tinto is a leading global mining and material company for over 150 years. It's been our DNA to find better ways as we strive for continuous improvement by facing challenges, finding solutions, celebrating our successes, and learning from the failures. As we look to the future, we're finding better ways to provide the material that the world needs. Today, we operate in 35 countries, where we produce iron ore, copper, aluminum, critical minerals, and other materials that the world needs for the global energy transition and for people, community, and nation to thrive. Globally, we directly employed almost 52,000 people, and we are dual listed in London and Australian stock exchanges. Rio Tinto Aluminium Pacific operates a fully integrated end-to-end aluminum supply chain and value chain in Australia, managing the entire process from bauxite mining through aluminum refining to aluminum smelting, and serving both internal and external customers each step with reliable and efficient deliveries of quality products. So through this integrated approach, we optimize operational efficiency while maintaining the flexibility to serve both internal downstream operation and external market demands, ensuring a sustainable value creation across the entire aluminum production chain. Rio Tinto Aluminium has strategically implemented AI across our value chain to drive operational excellence. So in power management, our FlexRod system optimizes energy consumption in smelting operation through real-time monitoring. Our ultra purity initiative leverages AI to enhance the metal quality while maximizing the production efficiency. So in raw material handling, we have developed a spectral data lake for advanced ore body analysis. So building on those successes, today we'll be focusing on our latest innovation, the integration of the generative AI into our technical training program. We'll explore how this technology is creating personalized learning experience and transforming the way we cultivate our workforce. Now with that, let me hand it back to you, Ben.
Thanks, Key.
Thank you.
So how often have you heard that large language models hallucinate? Pretty often, right? Well, part of that limitation is the data and how it's chunked when feeding LLMs context. So where do their answers come from? And when they do answer, what source did they use? This is not always clear when using them out of the box. Their answers are sensitive to different language used when prompting and can vary significantly depending on input and phrasing. How do you ensure their response is ethical and there's no bias in the output? Do you leave this to whatever the LLM was trained on, or do you confine it to your own data sets? And perhaps most importantly for the enterprise, having an understanding of domain knowledge is crucial for domain-specific output. On their own, LLMs struggle to provide accurate answers when asked complex questions. Organizations consider inaccuracy by far the most relevant risk when using Gen AI, and nearly a quarter have experienced negative consequences from inaccuracies. RAG, or Retrieval Augmented Generation, is now an industry standard, and it seeks to solve some of the limitations that exist with LLMs when operating on their own. RAG added domain context to large language models, giving them the ability to provide context-specific answers based on your own corpus of data. Conventional RAG usually involves a single data source, and generally, that's a vector database. However, this wasn't the silver bullet everyone had hoped for, but not for the reasons you may think. You see, traditional RAG relies on vector search to provide context, and this comes with some limitations. When you have a confined context window for a particular model, you can lose context, and related pieces need to be split apart to fit within that window. While KNN, or K nearest neighbor, effectively finds similar data points, enterprise search needs more than just embeddings. It requires domain adaptation, context-aware chunking, and business-specific fine-tuning for truly valuable results. Vector search on its own can lead to less accurate answers, even when using the latest algorithms. During the vector embedding process, trade-offs have to be made, and this can dilute precision of semantic representations, as they are effectively the average meaning of all words within each chunk. This can make it difficult to capture nuance and specific details within text. As datasets grow, the computational cost for processing high-dimensional vector embeddings increases. Rigidity arises from challenges scaling vector databases efficiently, as they require re-embedding and re-indexing when new data is added. And this is where GraphRag can help. A human view of an apple is what you see. A mostly round object, often red, textured, and easily identifiable as an apple. A vector representation of an apple is an array of numbers. When used during RAG, these are useful for finding similarity between words. You run a similarity calculation and you get a match. However, they lack an understanding of what's inside and around the vector. They cannot provide context for things represented in your text or how any of this fits into the broader context. Vectors are just not able to do that. A knowledge graph representation of an apple shows a real-world model, or in artificial intelligence language, a symbolic or declarative representation. The knowledge graph inside a graph database represents the domain you are working with in a way that humans and machines can understand, using nodes and edges to represent connections. Graphs digitize text by associating indices to each character or word and represent text as a sequence of these indices. Graphs excel at traversing relationships between data, such as Superman, who is in a movie, and the Titanic, which is a movie, and these have a relationship of movies. By combining large language models and graph databases, you leverage the benefits of data accuracy and structured knowledge, whilst removing some of the LLM's limitations in hallucination and lack of domain-specific knowledge. So why not combine them all? Vector search, knowledge graphs, and LLMs together to give you hybrid RAG. A hybrid approach to question answering combines the best of vector similarity and graph searches to optimize performance for RAG applications. By integrating these two retrieval systems, we're able to use both structure precision and semantic flexibility in handling intricate queries. The output is more accurate, context-aware, and enables more complex queries because of the inclusion of a graph database. Knowledge Bases for Amazon Bedrock is a fully managed RAG capability that supports hybrid RAG out of the box. Knowledge Bases automates the end-to-end RAG workflow, including ingestion, retrieval, and prompt augmentation, eliminating the need for you to write custom code and to integrate data sources and manage queries. All the information retrieved from knowledge bases comes with source citations to improve transparency and minimize hallucinations. Now let's hear from Key from Rio Tinto on how they leveraged Amazon Bedrock and hybrid RAG to provide access to their enterprise domain knowledge.
Thanks, Ben. So in Rio Tinto Aluminum, we are running internal training program to enhance the technical skill of the employees in refining and smelting sectors. So our technical experts in refining and smelting sectors are facing critical challenges in access vast amount of specialized knowledge quickly and accurately when needed. So to address this, we've enhanced our training program with generative AI-powered knowledge system that to provide the employee instant access to institutional knowledge and streamline how business find and utilize critical business information. So from the previous discussion, we have learned together the potential benefits of what the graph database can bring to the generative AI implementation. Let me show you how Rio Tinto has turned this potential into reality with our innovative hybrid search system. So the hybrid search system we developed consists of 4 main components: the knowledge graph, a vector indexing, retrieval system, and the generative AI models. Starting with the 2 parallel components, the knowledge graph stores data in a graph format, where information is captured as the connected entities and the relationships. Alongside it, the vector database identifies and understands those entities and the relationship through semantic embedding, enabling semantic search for those graph data. Those 2 components work hand in hand. While the graph shows how things are connected, the vector helps us to understand what they mean. Our retrieval system then leverages both components, combining the graph traversal with the semantic search to find the most relevant information. Finally, the generative AI model takes its own retrieved context to create coherent and meaningful responses. Now that we have covered how the hybrid system works in theory, let me show you how we implement this in AWS Cloud. So here's our hybrid solution architecture design. The design is constructed into 2 primary layers. First is the data ingestion layer. At its core, we have 2 Lambda functions. The first Lambda function handles the raw document processing and the context extraction. The second Lambda function performs 2 critical tasks. First, it builds and maintains our knowledge graph by establishing data connections. It also generates semantic embedding to power the vector search capabilities. Now, what's important to know here is that those 2 Lambda functions leverage 3 main components from our hybrid search system: the generative AI model for text embedding, and the vector indices, and the knowledge graph as data storage. So built on the service technology, this entire pipeline scales automatically as the workload demands. Now let's explore the second layer of our architecture, the hybrid text generation system. Our hybrid retrieval system runs on Amazon ECS to ensure its reliable performance, where it performs 3 main functions: a vector similarity search operation, graph-based context retrieval, and text generation. It's worth noting that we also enhanced our system using Amazon Bedrock knowledge base service, providing additional vector-based RAG approach for more flexible user interactions. Now that we covered the high-level design, let's dive deeper into how each layer works in detail. So in the data ingestion layer, our document processing begins with a specialized approach to format handling. So for rich formatted documents, we first convert them into images. Using the vision capability from Amazon Bedrock multimodal models, we extract comprehensive information from text and table to visual context, so transforming everything into structured text. From there, we then perform chunking on those extracted texts. We implement a semantic chunking as a preserve meaningful content by breaking the text into coherent and logical units, which offer better contextual understanding, therefore help to increase the overall retrieval accuracy. Next, we use a text model to analyze each chunk, performing entity recognition and the relationship extraction to produce our knowledge graph. The embedding model vectorizes the text representation of each graph element and store the vectors into the vector database. So this data ingestion pipeline allows us to capture both the semantic meaning and the structural relationship, creating a robust knowledge foundation for our hybrid search capability. Now, having established our knowledge foundation, let's explore how we leverage this dual structure to deliver accurate and contextually rich responses. So in the text generation process, first, the user will submit a technical question. Our system performs two initial operations. First, it will analyze and reformulate the query within its conversational context, aligning with our specific domain knowledge structure. Then we search the vector database and identify the most semantically relevant matches. Next, we process the entity data and determine their relevance. Starting with the entity discovered from the previous vector search result, we use a matched result to traverse the graph database and gather three main important pieces of context: the entity's consent summary and the original document where entity was first identified. Now remember, in our graph database, each entity node is connected to others through various relationships. So in the third step, we query those connections to map out what we call the first-degree relationship. So in simple terms, they are the direct connections between the entities. Now before we move on, there's one crucial question need to be addressed. So how can we find exactly what information matters the most to the user's question? So our approach is very methodical. We determine source entity's relevance score through a smart re-ranking process. The following are the steps. So first, we locate the target entity through our first-degree relationship, and we compute the vector semantic score between the target entity with the user query. Finally, for each source entity, we produce a relevance score by summing the vector semantic value of all the related target entities. Similarly, we quantify each first-degree relationship's relevant score by calculating the vector semantic score within the user query as well. So what makes our system particularly effective? It's contextual weighting. So instead of treating all the information equally, we prioritize the context based on its relevance against the specific user question. So this intelligent weighting ensures that our response are both comprehensive and precisely focused on user intent. Now let's break down this with a simple example you can easily follow. Imagine user asks a question, how to fine-tune a foundation model in Amazon Bedrock. So here's our system processes. First, we locate the most relevant entities from our vector database. Just for simplicity, I'm only showing the top three match result here. From the vector search result, so we identify the same entity from the graph database. So for each of those entities discovered from the graph database, we perform a graph traversal to discover their first-degree relationship. For each of the connections we found here, we then calculate the vector similarity score between the target nodes and the user question. After calculating all the similarity score for each of the target entities, we add them up to create a weighted score for every source entity. Next, we extend our scoring process to the relationships themselves, compute the vector similarity score for each of the connections. Now, by using this re-ranking method, we essentially giving the model smart instructions to pay more attention to more relevant entities like the foundation model and its relationship with Amazon Titan models, giving low priority to less relevant information like the technical API details and its connection, say, to the cross-regional influence, for example. So the result, we're helping the larger model to focus what really matters to the user. So in this case, it's the information about the model fine-tuning rather than just getting lost in the technical details. Now let's bring back to the text generation process and continue the second phase, the relationship data processing. So to process each relationship, we follow the similar steps how we handle the nodes. First, we extract the relationship summary along with its original context. So when we calculate the relevance score for each relationship, we can optimize this step by directly referencing the ones already obtained from the initial vector query, avoiding the need for recalculation. Now again, in our graph database, every relationship comes with a source node and entity node, target nodes. From there, we identify all the connected nodes and retrieve their corresponding entity summaries. For the final step, we determine the entity relevant score by using the same re-ranking process that we introduced earlier. Now let's bring everything together for our final response. We will create an augmented prompt by combining the three key elements: the context extracted from the databases, prioritized by the relevance score, the refund user query, and the session chat history. This combination allows us to generate response that are both comprehensive and contextually precise. Now to see those principles of action, let me walk through a demonstration. So in this demo, we'll compare two rack systems using a typical question from a Rio Tinto alumina refinery. Let's walk through a common operator thought process. So in this case, the operator first inquires about the flocculant preparation process in the alumina refinery and try to understand its downstream impact if it's not performed correctly. Then naturally progress to the monitoring protocol that is needed to meet the business standards. Now we process those questions through both rack systems and examine their response side by side. Now, looking at the table, we can observe some key differences. While both systems addresses process detail and the troubleshootings, notice our hybrid rack system posing substantially more detailed information in those areas. It also provides significantly more comprehensive information in other critical aspects, particularly in the areas such as the critical control and equipment specifications. Now, a key distinction lies in the technical depth. The vector rack typically draws from 2 to 3 sources, while the hybrid rack leverages 11 to 17 technical documents per query, providing far richer context. Now for operational team, this translates to the enhanced process control, quality standards, equipment specification, and better problem-solving protocols. So in short, the hybrid rack's superior technical depth and practical relevance deliver significantly more value to Rio Tinto's alumina refinery operations. Now we also evaluate both rack systems at scale, where we use a technique called the large language model as a judge across 100 industry-specific questions, and the results are compelling. The hybrid rack system significantly outperforms its vector counterpart across all metrics, especially in the context quality and the context entity recall. Now take a look at the density distribution graph on the top right. The pattern is clear. Notice how the hybrid rack score cluster tightly in the higher range, while the vector rack results spread more widely across the low range. So this demonstrates that our hybrid rack isn't just performing better, it's doing so with remarkable consistency. Now the stability of the hybrid rack system is also impressive. We observed over 53% reduction in standard deviation for key metrics like the context precision and the context entity recalls, while maintaining a high mean score across all measurements. So the bottom line is clear. The hybrid rack delivers higher accuracy and greater reliability when handling complex industrial questions. Now let me wrap up this talk by highlighting some of the technical decisions we made behind the system design. First, we chose Amazon's Titan text embedding model for 2 reasons. First, it is specifically designed for the rack application, and its strong multilingual support that align with our future expansion plan. Our search infrastructure combined the Amazon's open search service with Facebook AI semantic search engine, creating an elegant and efficient vector search solution using Amazon Titan's normalized embedding. Second, our rule ranking system is highly adaptable, meaning that we can easily adjust the search radius based on the knowledge structure. And most importantly, within a fixed search radius, our text generation is deterministic, ensuring that a consistent text retrieval for identical queries. We also implemented a clear domain knowledge separation in both storages, improving the access control and better search precision. Finally, to boost the system performance, we implement a smart caching approach that works on multiple levels. It stores both frequently accessed system data and common users' question and answer pairs, significantly reducing the response time and creating a smoother user experience. Now that is an overview of the hybrid system developed by Rio Tinto. Thank you very much for listening, and I'll pass back to you, Ben.
Thanks, Key. It was remarkable. Hybrid retrieval, augmented generation, and Amazon Bedrock allows organizations access to accurate, verifiable, deep domain knowledge. Above is an example of an enterprise search pattern using hybrid RAG to exploit the benefits of graph explicit relationships and vector, filling in the relational gaps and enhancing context structure. Now, while Rio Tinto used Neo4j, Amazon Neptune works similarly for hybrid RAG and is supported out of the box as a knowledge base on Bedrock. And to wrap up the session, hybrid RAG unlocks the true potential of large language models by combining the best of vector search and graph databases. We recommend starting with a separate knowledge base for each domain to ensure a good fit for your outputs and ensure guardrails against intellectual property can be applied easily. Using the inbuilt Titan text embedding models ensures multimodal embeddings out of the box and multilingual support from the get-go. So you don't have to start all over again when you add more language support. And if you want to start straight away, you can leverage Amazon OpenSearch Serverless and Amazon Neptune for vector and graph databases out of the box and be building your hybrid RAG solution in minutes. Technology makes innovation possible, but it's people who build a better tomorrow. Your time is now. On behalf of myself and Key, we thank you so much for listening today. We're available at the front of the room to take questions, and we have some swag to give away. Please take a moment to answer the survey and enjoy the rest of Summit. Thank you.
Thank you.
Thanks, mate.